Silakan. MC kita bisa dimulai.
Oke, Assalamualaikum warahmatullahi wabarakatuh. Shalom, Om Swastiastu, Namo Buddhaya, Salam Kebajikan. Good afternoon, ladies and gentlemen. Welcome to Marine Science Webinar 2022. We are proudly present an overview of the Peruvian upwelling system, physics, biogeochemistry, fisheries, and its response to the climate change. It's been a great honor for me, Putri Fancy, as a Master of Ceremony, and welcome each and every one of you in today's webinar. For a few hours, this webinar will provide you plenty of opportunities to discuss, share knowledge, and insights. Before we proceed to the main session, we would like to express our sincere gratitude to our Dean of Faculty of Fisheries and Marine Science, IPB University, Dr. Ferdinand Yulianda, Head of Graduate School of Marine Science, Faculty of Fisheries and Marine Science, IPB University, Dr. Beginner Subhan, our keynote speaker from L Ocean Sorbonne University, Professor Dr. Vincent Chevin, and our moderator from Department of Marine Science and Technology, Faculty of Fisheries and Marine Science, IPB University, Dr. Agus Saleh Atmadipura. Last but not least, we would like to express our sincere gratitude to our invited guests and participants in today's webinar. Before we move to the next session, we will hear a national anthem of Indonesia Raya. Okay, next we will hear a welcoming speech. Firstly, we would like to invite Dr. Beginner Subhan as the head of Graduate School of Marine Science to deliver his welcoming speech. Mr. Beginner Subhan, the time is yours.
Thank you very much. Good afternoon, everyone. Our Excellency, Dean of Faculty of Fisheries, and Marine Science, Dr. Ferdinand Yulianda, Dr. Agus Atmanipura, and Dr. Vincent from Sorbonne. Thank you very much for your time, yeah, to give speech. So, Pak Dekan, this webinar is part of graduate school, a graduate course, the upwelling systems, IKL 725 at the graduate program in Marine Science, graduate school, IPB University. And Pak Dr. Agus Atmanipura is the initiator, yeah, of this webinar, and I think this is a good opportunity, yeah, for us, yeah, in Indonesia, learn how the Peruvian upwelling systems, yeah, and I think Professor Vincent will talk comprehensive speech, yeah, about the physics, biochemistry, also fisheries, and climate change. I think the upwelling system also important, yeah, in Indonesia related to fisheries, yeah, and also climate change. So actually, this is like also a kick-off, yeah, kick-off of webinar, Marine Science webinar. So this is the first, and we are already planned the sequential webinar, yeah. So every 2 weeks, we will invite speakers from different topic, yeah. So for next week, next 2 weeks, we will invite Dr. Reza Korova and Dr. Neviati for give talk about the marine debris, and then next month Edi Setiawan, yeah, PhD student from Auckland University, New Zealand, will talk about the how to measure size of manta using drone image. So we are also open, yeah, to researcher, yeah, in Indonesia or abroad to give a speech in marine science webinar. So for the last, we are send our gratitude for all the participants who participate this webinar. We hope this seminar will give insight, yeah, for us about the marine science in general and upwelling systems in special terms. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Good morning and good afternoon. Thank you.
Okay, thank you, Mr. Beginner Subhan, for the speech. Next, we will hear a welcoming coming from Dr. Ferdinand Yulianda as the Dean of Faculty of Fisheries and Marine Science, IPB University. Mr. Ferdinand Yulianda, the time is yours.
Pak Dekannya hilang sinyalnya kayaknya. Halo.
Okay, it's a problem.
Hilang sinyal.
Okay, yeah. Thank you, Putri dan Chin. Yeah. Assalamualaikum warahmatullahi wabarakatuh. Dan good afternoon and good morning for Professor Vincent. The Honorable for Professor Vincent and Sehin. Yeah. I'm sorry if I made mistake to spell your name. From Sorbonne University, Paris, and also our speaker, Dr. Agus Saleh Atmadipura, and also all participants of webinar. I respect also the representative chairman of the Department of Marine Science and Technology, Dr. Begin. Yeah. So on behalf of IPB University, I'm Ferdinand Yulianda, the Dean of Faculty of Fisheries and Marine Science. Very glad to welcome all the participants of this webinar. So growing issues of marine sciences and climate change in marine resources management aspect in recent years has led marine science researcher to pay particular attention to this subject. Yeah, the climate change, the threat of rising sea level, environmental and pollution, and dynamic of life under the sea are interesting phenomena to discuss by experts. Yeah. This webinar is for forum for scientific experts. Yeah. Include the part of undergraduate program, as Dr. Begin said, to contribute their mind to dealing with marine natural phenomena, and recommended several strategies to manage natural resources, let's say, and marine environment. Faculty of Fisheries and Marine Science, IPB, through the Department of Marine Science and Technology, has anticipated the issues of the climate change through an overview of the Peruvian upwelling system, physics, by geochemistry, fisheries, and its responses to the climate change. So what we have done in the Department of Marine Science and Technology perhaps can be enriched and strengthened by the experience of the speaker, especially Dr. Agus Atmadipura, and also student of Marine Science and Technology program. Hopefully, at the end of this webinar, will produce some recommendation for the how to manage marine resources on the earth. Please enjoy to the webinar. Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum warahmatullahi wabarakatuh.
Okay, thank you, Mr. Ferdinand Yulianda, for the speech. Before we move to the main session of the webinar, we will take a photo together. So for all the participants, maybe can turn your camera on. So we will take your screenshot on this webinar. So there will be 3 slides in this Zoom meeting. Maybe the operator can take a screenshot of all the participants. For the first slide, 1, 2, 3. Next, we move to the second slide. 1, 2, 3. Next, the third slide. 1, 2, 3. Okay. Okay, maybe that's it for the photo. Now, we come to our main session for today's webinar, who will be led by our moderator, Dr. Agus Saleh Atmadipura from Department of Marine Science and Technology, IPB University. Mr. Agus Saleh Atmadipura, the time is yours.
Thank you very much, Putri. So I'll share some slides here. Can you see this slide?
Yes, Pak.
Okay, thank you. So thank you very much. Good afternoon, ladies and gentlemen, all participants in this Marine Science webinar. And also good morning, Professor Wang Sang, Josephine from Paris. So I'd like to present here the introduction for before the presenting Professor Wang Sang lecture. So this webinar, as mentioned by Dr. Begina Subhan, this is a part of graduate courses with the title The Upwelling System. And today we invite Professor Wang Sang. So he's a distinguished professor from Lausanne Sorbonne University with the title of this lecture is The Peruvian Upwelling System, discussing of physics, biogeo, fisheries, and also its response to the climate change. So I'm glad to be your moderator this session. So it is just one slide to remind you that our ocean also has the many spot area of the upwelling here. For example, from the western part to the eastern part, with the most well-known is southern Java, and also here is Banda Sea and Arafura and Arusi and so on here. But here I think if you can tell that the upwelling here is seasonal. That means this appear during a particular season and this appear during the opposite season. And also possibly be alternating upwelling downwelling during different monsoon period. So in this seminar, we would like to to adopt the lesson learned from Professor Wang Sang, who he so many doing research in Peruvian upwelling system, and I think he will deliver the letters. Yeah. And also after this speech, I think Professor Wang Sang we can discuss or to take the conducting the prospective research collaboration. So here, Professor Wang Sang, he is the IRD senior research scientist. IRD, this means Institute Research for Development. This is one institution taking the research center in France, among the CNRS and so on here. So Lausanne is composed of the unit mixed research with etc. CNRS, IRD, Museum National Histoire Naturelle, and also Sorbonne University. And I think if you are interested to this Lausanne, you can access this website, yeah, Lausanne IPSL UPMC. And Professor Wang Sang is I think this researcher, a very well-known researcher in Lausanne. So his interest in physical biological functioning coastal upwelling system, and also is a very excellent in expertise in ROCO modeling. This is the system modeling, ocean modeling, and also PCES. This is a biogeochemical models. I think Professor Fang Sam will tell more detail later. Also observation system. So here is, for example, indexes in Scopus. So his index is 28, ASH index. And also this is the Google Scholar index. I think it's very well-known researcher here. And this experience for Professor Fang Sam is so many projects, national, European, and international, as you listed here. And also is supervisor from master, doctoral, postdoctoral, and also is the examiner or rapporteur with 18 juries in France and international. And this is the lecture activities of his conducted at Lausanne. So the lecture session will be divided into 4 sessions. This is session 1. He will deliver about 45 minutes courses, and also time break 10 minutes that we will utilize to video presentation of our department. And then session 2 will continue 45 minutes for the course. And the last session is for comment, question, or suggestion. You can also post the question. You can ask question via chat, yeah, in this webinar. So this is the introduction for Professor Fang Sam. And now it's time is yours. Thank you very much. I stop slide here.
Okay, good afternoon, everyone. Can you hear me?
Yes.
Okay, so thank you very much for inviting me to give this webinar. I'm very honored. Okay, I will try to share my screen. Can you all see my screen?
Yes. Yeah.
It's in full screen.
Oh,
This is slide presentation.
Yes, this is a slide presentation, but is it in full screen?
No,
no.
not yet. Not
No.
yet.
Ah. Okay, wait, maybe
The diapo, no?
in diapo mode. Yes, now it's in full screen. No.
Okay. Yes. Yes. Thank you.
Okay, so thank you very much again. So I want to acknowledge the institute that is funding my research, is the IRD. So IRD is a French Institute of Science, but its main goal is to collaborate with countries from the global south. So we have a lot of collaboration with South America, Africa, and also Asia. For instance, Ariane Kochelaroui, who you may know, is also from IRD. So as been told, I have worked for almost 20 years now on the Humboldt system with Peruvian but also Chilean colleagues, and I will mainly focus on the Peru upwelling system in the presentation. Okay, so the Peru upwelling system is one of the 4 eastern boundary upwelling systems, which are called also EBUS. So you will see this notation throughout the presentation. So upwelling systems, there are 4 main upwelling systems: the California EBUS, the Canary EBUS of Western Africa, the Benguela EBUS of South Africa, and also, of course, the Peru-Chile EBUS of the Peru and Chilean coasts. So these EBUS, they share the common characteristic that they have a very high, the chlorophyll concentration in the surface water is really high. So this is what you can see on this satellite image, which is the mean concentration of chlorophyll seen from space. And you can see this yellow band near the coast corresponding to high concentration. So in these regions, there is a very intense biological activity. And also, because of this biological activity, there are very productive fisheries. And if you count the total catch of fish over the entire planet, 20% is from these eastern boundary upwelling systems, where over a very, very small surface, which is around 1%. So they are very, very productive. Among these EBUS, Peru is the most productive EBUS. It has the highest fish catch, and it produces almost 30% of the total fish oil and flour. So the kind of fish that is captured in this region is relatively small fish, like sardines or anchovy, and it's not principally used for human food. It's more or less transformed into oil and flour that is used then for agriculture. And so if you look on the right side here, you can see on the vertical axis the fish production, the fish catch production, and on the horizontal axis the primary production, which is the plankton production. And you can see that Peru is not the most productive, does not have the most productive primary production. In fact, it is Northwest Africa, which is mostly productive. But if you look at the fish production, there is a very, very high production. It's almost 10 times stronger than the other systems. So this is kind of a paradox, and I will come back to that later in my presentation. The Peru region is really extremely productive. So there is also a very strong variability of its fish resources. So in this figure on the bottom, you can see a long time series of seabirds in black, anchovy in blue, and sardine in red. And you can see that there are very large variations at decadal time scales, but also at shorter time scales. For instance, I have highlighted the strong decrease of anchovy during El Nino events, the El Nino 2002-2003 and the El Nino 97-98 that were very strong. And you can see that the anchovy production decreased a lot. So this very high variability is also something that we have to be careful about. So just maybe some generalities about upwelling systems. So these upwelling systems are mainly forced by the wind. So here is the surface pressure and wind, surface wind map in July from a relatively old product, the N7 climatology. And you can see that the upwelling, the EBUS are located on the eastern flank of the high pressure systems. For instance, here and here in the north hemisphere, and here in the south. And because of this location, they tend to be
semua apa orang 70.
Ori, can you turn off your mic?
70%.
So because of this this location, they tend to be okay. Can you hear me? Yes.
Yes.
So I continue. So these high pressure systems have winds on the sides, and on the eastern flank, the winds tend to be parallel to the coast, which drive Ekman transport offshore, and then there will be upwelling. So this is what is sketched in this simple schematic. So here you have on the coast the Andes, the mountain chain of South America, and here you have in these red arrows mark the winds that are parallel to the coast, and so these winds, they drive surface currents offshore, and here is sketched the Ekman spiral. So if you integrate over the Ekman layer, which is represented here, this current, you have a net offshore transport, which is called the Ekman transport. Okay, and this net Ekman transport of water brings an upwelling of water near the coast because of the mass continuity. You have to, if you take mass away from the coast, you have to take mass upward near the coast. So there is an upward flow of deep water, and these deep water are cold and nutrient rich. Okay, there is also another process for upwelling, which is called Ekman pumping. Because the wind is not completely homogeneous, you have a variation, a cross-shore variation of the wind. If you look at the wind near the coast, it tends to be weaker than the wind offshore. This shear of the wind tends to drive a variation in the Ekman transport. So near the coast, you will have a small Ekman transport because there is weak wind. And slightly offshore, you will have a strong Ekman transport because there is strong wind. Okay, so in between, because again of this mass budget, you need to have upwelling of water here to compensate this Ekman transport. So this process is known as Ekman pumping. So in upwelling region, you have very strong upwelling near the coast, but you have also less strong, but over a wider region, you have also Ekman pumping. So this is something to take into account in Ekman regions. So let's talk now about biogeochemistry. On the left side here, you have a basic nutrient profile, for instance, nitrate. And you all know that nutrients are very low in the surface layer, and they generally increase at depth because of remineralization of the organic matter in the ocean. Okay, because you have upwelling, so you have a vertical flux of water that are cold and that are deep, and these waters have a lot of nutrients, and so when you bring this nutrient-rich water in the surface layer, this surface layer also has a lot of light, because light propagates from the top of the surface layer and then gets absorbed in the surface layer. So because you have light, nutrients, and also you have CO2, which is dissolved in the atmosphere, you have everything that is necessary to produce plankton, this process is called primary production. And so you have photosynthesis and plankton growth in this surface layer. This is why the upwelling systems are very rich near the coast. Okay, so this is a particularity of the Peru upwelling system, is that it has a very intense oxygen minimum zone below the surface layer. Why is there an oxygen minimum zone? Well, first there are some physical reasons. It's because at subsurface near the coast, the concentration, the circulation is very slow and very weak. So this water is very old, and when the water is old, its concentration in oxygen gets low. But also because you have a lot of productivity in the surface layer, which is represented here by these green patches. This organic matter, plankton, zooplankton, and also fish, when it comes to the end of its life cycle, this organic matter tends to sink to the bottom of the ocean. And so bacterial activity tends to remineralize this organic matter in the subsurface layer, and remineralization, during the course of this remineralization, these bacteria need oxygen for respiration. And so they tend to consume oxygen. So in the Peruvian upwelling system, in fact, you have very high productivity, so very high consumption of oxygen, and the oxygen concentration can get close to zero, okay? And also because it is very intense, the oxygen gets close to zero very near the surface layer. But sometimes at around 50 meters, you can have zero concentration of oxygen in the Peru system. And even in some region, the very low oxygen waters can rise to the surface. So this is a very important constraint for the ecosystem, because a lot of species, most species need oxygen to survive. So in fact, their habitat will be constrained in the very shallow surface layer, represented here by these dark arrows. Okay, so I will come back to this also later when I will talk briefly about fisheries. Okay, now a few words about this oxygen minimum zone. So here in color, you can see the oxygen concentration average over the subsurface layer between 100 meters and 300 meters. And you can see that along the Peru coast and slightly offshore, and also North Chile here, you have concentration around 10, 20 micromoles per kilogram, which is really, really low. Very, very not favorable for marine life. Here is a mean profile over a box. So you see here this black box, which is a coastal box. What we did is to take all the measurements in this region and average them together. And then you obtain these red bars. So the bars mean the variability. And you can see the concentration decreases very strongly, and it's almost zero in this region. Okay, so now let's go back a little bit to the dynamics or the physics of the EBUS. In fact, EBUS are not simple systems; they are very dynamic systems, and there is a lot of variability. For instance, here in green, there is a front separating the cold and warm water, and these fronts are very unstable and they can meander, etc. So the circulation represented by these black arrows is relatively complex. There are also a lot of eddies that tend to propagate offshore, westward, and they tend to influence also the upwelling front. So this is, to illustrate that, I show this a picture of a model simulation with a high resolution at 500 meters here. And you can see that you have these cold waters in blue near the coast, corresponding to the upwelling. And offshore, you have these red waters, which are warmer. And in between, you have a lot of small scales, and you can see that there are filaments of cold water and warm water that are intertwined together. So it is a very dynamic and complex system. Now, if we look at the vertical structure of the currents, we have already seen the Ekman flow in the surface. Because there is a strong gradient between cold and warm water, you have a density gradient and also a surface jet here that is in the Peru upwelling system. It's a northward jet. And below, what is typical of all upwelling system is the undercurrent. So there is an undercurrent, which is around between 50 and maybe 200 meter depth. Also below, there are other jets that are less well known because we have not a lot of measurements at these depths in these regions. But there is a deep undercurrent has been measured at some occasions. Okay, to give you some information about the data. So here, a lot of ADCP measurements were taken in this black box and averaged together to obtain like a mean undercurrent. And this is what you can see on the right side. This is the Peru-Chilean undercurrent. It's between almost nearly, sometimes it can reach the surface, in fact. So it's between 20 meters until 500 meters. And it's really trapped along the slope, and it can also penetrate on the shelf. And its maximum velocity is not very fast. It's around 8-10 centimeters. Let's have a bigger view of the Peru upwelling system. So we have seen the Peru undercurrent, which is sketched here by this red arrow here, the PCUC, Peru-Chile undercurrent. And what is really important in this upwelling system is that it is close to the equator. And so there is a strong connection with equatorial current. These equatorial currents are the equatorial current, undercurrent that is really at the equator, the equatorial undercurrent, which is sketched here. It is deflected to the south and also to the north because of the Galapagos archipelago, which is really close to the equator. And also, very importantly, these two jets, subsurface jets, tend to bring water towards the upwelling system. Here, the subsurface countercurrent. So they are really important because they tend to bring also oxygenated water towards the Peruvian OM oxygen minimum zone. If we look at the section here, so it's really difficult to see in these observations because these jets are very, they move a lot. And so we don't have a very clear image of their location. But if we take ocean models and we make an average of a long time, you can really see the EUC here and these two jets, the two subsurface countercurrents here and here. And they tend to be, this one tends to be more intense than the other one. Okay, so what another particularity of the Peruvian EBUS is that it is very close to the equator, as I said, and also it's in the Pacific Ocean. So we have this huge climatic anomaly, which is called ENSO, El Niño Southern Oscillation. So just a few words of how the ENSO works. I will not go into the details here. So generally, you have some easterly wind bursts in the Western Pacific, in this region. And these wind bursts, they tend to trigger equatorial Kelvin waves. They are downwelling Kelvin waves, which means that they tend to deepen the thermocline in this region, which explains the warming here at the surface. And when they reach the coast, this equatorial Kelvin waves, they generate coastal trapped waves that propagate along the coast. And these coastal trapped waves, they generate the Rossby waves that tend to propagate westward. So you have really a strong connection of waves along the coast, from the equator here, along the coast, and then offshoreward, which takes place in the Peru and Chilean system. So now this is the main outline of my talk. So I will talk a lot about the physical forcing and its impact on the Peru ecosystem. As Agus said, I'm mostly a physicist at the my PhD was on physics, and then I was really interested in biogeochemistry. But I will talk finally little about fisheries because it is not my specialty, but I will say a few words near the end. So first, I will talk about the tools that we have in the Peru upwelling system to study this system, observations, and also the models. I used a lot of the models, so I will insist a little bit on this. Then I will talk about different particularities of this system, the impact of the wind cross-shore variability on the productivity, the impact of the wind seasonal variability on the productivity. This is a very special case for the Peruvian system. And I will also talk about the impact of coastal trapped waves and of El Niño variability. El Niño variability has a very strong impact in the Peruvian system. And then I will talk about the influence of climate change in this system in the recent past, the recent decades, and also in the future, using climate scenarios, for instance. And then I will briefly talk about fisheries and come back to the question, why is the Peruvian EBUS so rich? And then I will just have a few open questions and perspectives. Okay, so what kind of observation do we have? In fact, in Peru, there is a lot of in situ observation thanks to the Peruvian Sea Institute, El Instituto del Mar del Perú, or IMARPE also. And this IMARPE is a rather old institute. It has been created in the 50s, and it collects data, a lot of data since then. So in fact, there is a very good database of oxygen, and there is a database also for surface chlorophyll. Here is, for instance, a climatology we did a few years ago. But there is also temperature, of course, salinity, nutrients, and also there is a more recent database of ADCP currents because they have ADCP on their research vessels. More recently, we did with these Peruvian colleagues some glider experiments. So glider data has been collected in some regions, and gliders, as you may know, they allow you to have an almost synoptic view of the ocean, and also some very high spatial horizontal resolution of the data. So you can see some very small scales. There is also, of course, satellite data, for instance, sea level altimetry to look at sea level and surface currents, wind from scatterometers, QuickScat, ASCAT, and other satellites, and also, of course, sea color data to look at chlorophyll, for instance. As I said, I used a lot the models. So we used physical models to study the physics, and a model that we use is it was previously called ROMS, and now we use a more modern version, which is the CROCO model. And here I give you an example of the kind of grids that we used. So we generally use a grid that takes into account all the Peru region. For instance, this is the grid at 10-kilometer resolution here. But then we embed some small scale grids with a higher resolution, 2.5 kilometer here, for instance. And here for a particular study, we studied a bay here with a grid at 0.5 kilometer. So this is the general strategy that we have. We also used a lot biogeochemical models, and in particular the PSCES model. So I will take a few minutes to describe this model because I will talk about it throughout the presentation. So the PSCES model is a model of models the cycle between nutrients, phytoplankton, zooplankton, and then organic matter. It is interesting because it represents the cycles of several nutrients, nitrate, ammonium, so for nitrogen, but also phosphate, silicate, and iron. Iron can be important because it can be a limiting nutrient in Peru or in other IBUS. Phytoplankton, so it's relatively simple models because they have only two groups, like big phytoplankton, diatoms, that are the main species in Apoling systems, and a nanophytoplankton, so smaller phytoplankton. Then you have zooplankton. And what is important is that these living compartments, they produce organic matter that is sinking in the ocean. So we have small particles and big particles. Of course, what is really important is that we have also the oxygen cycle, which is represented in this model. So oxygen is produced by photosynthesis when phytoplankton is produced. It is mixed when there is contact with the atmosphere. So there is a source of oxygen from the atmosphere. And it is consumed by respiration of zooplankton and by remineralization by bacterial activity. Okay, so what is the strategy that we have for these regional models? So these regional models, as you can guess, they are open to the global ocean. So in red here is the model domain, and you can see that you have this boundaries here that are open, and we need some conditions to force the models. And these conditions, they generally come from other larger scale models that have a smaller resolution. So the resolution can vary between 25 kilometers and be up to 200 kilometers for the global models. And for the high resolution regional models, it can be between 1 kilometer to 20 kilometers. So the physical models, what they calculate are the currents, temperature, but also the mixing coefficients and the light profiles that are really important. And this is really important because they use all this information to force the biogeochemical models. And then the biogeochemical models, they represent a series of processes, for instance, photosynthesis, respiration, permeabilization, but also grazing by zooplankton, for instance. Okay, so what kind of data do we use? How do we use this data, to evaluate our models? Well, for instance, we use a lot sea level to study the eddy kinetic energy of the models. It's important because this eddy kinetic energy gives you an idea of the intensity of the eddies in the model, and if the model is able to represent the relatively large scale eddies, mesoscale eddies, in a correct way. So here you have a map showing that the model is able to represent the relatively high eddy kinetic energy all along the coast here, comparing to the observations. We use a lot of this temperature to study the stratification. Here is a mean cross-shore section of temperature, and you have this characteristic in upwelling systems with the isotherms, isolines that tend to be closer to the surface near the coast. This is a typical signature of upwelling, and you can see that in the model we represent this relatively correctly in comparison to these observations. We also use, of course, this surface chlorophyll from satellite, and here is a comparison with the model. We can see, as I showed in my first slide, that you have a high concentration of chlorophyll near the coast, and then it decreases, so there is a strong gradient. And the model is able to represent this strong gradient here with some bias, of course, and models are never perfect. So here we have a slightly too high concentration of chlorophyll near the coast in the model. And we also use nutrients to compare with the model. For instance, here we have this cross-shore surface nutrients. So the cross-shore are represented by these black sections here that are averaged. And so we have a relatively good comparison between the model and the observations. The model is in black and the observations are in red. Okay, so now I'm coming to the first kind of study that we did to study in the Peruvian IBUS. And what we did is to try to investigate the wind stress variability and its impact on primary productivity. So what is the problem here? The problem is that the wind stress is not very well known near the coast. And eastern boundary upwelling systems are mainly driven by winds, by coastal winds. Here is an example of wind profiles from models. So this is not in Peru, but this is in California. So on the right side, you have the coast. On the left side, you have offshore, and this is a distance in kilometers. And these lines are different wind stress profiles from different models. And you can see that the different models represent very different wind stress profiles. And for instance, the small scale model here at 3 kilometers, these are from atmospheric models. They have very steep variation of the wind stress near the coast. This is called the wind drop-off. And the problem is that this wind drop-off, this variation of the wind near the coast, is not well known, and atmospheric models, they don't seem to converge with the resolution increase. So this is a large uncertainty in upwelling systems, and we have to see, we try to see what is its impact on the productivity. Okay, so yes, there is a problem with the model, but there is also, as I said, the problems with the observations. The wind structure is not well known near the coast because there is lack of data. There's generally very few meteorological stations available. And also the satellites do not see the wind near the coast. There is what is called a blind zone. On this picture, you can see the blind zone in white. So we have no data very near the coast. And this is a problem when we use models because we need to extrapolate the data near the coast. So what we did is an experiment where we used two different wind stress, one which has a strong drop-off and one which has a weak drop-off, meaning that the variation near the coast is very weak. And what you can see here is the response of the current system due to these two wind variations. So these wind variations are really the same offshore. So the change are really due to the wind profiles in the 100, 200 kilometer band near the coast. You can see it has a really strong impact on the surface jet. When you have a strong drop-off, the surface jet is relatively shallow. When you have a weak drop-off, surface jet is very strong. And it has also an impact on the undercurrent. You have a very strong undercurrent when you have a strong drop-off, and a weak undercurrent when you have a weak drop-off. So there is a really strong impact on the wind drop-off on the alongshore currents. And this also impacts biogeochemistry. So for instance, here, what we did is to study the pathways of the waters that are upwelled, meaning that in the model, we are able to follow the water mass that is offshore and that comes to the surface in the upwelling system. And here, what we did is to look at the concentration of the water mass that comes to the upwelling system. In black, you have the concentration when there is a strong drop-off, and in blue and green, you have the concentration when there is a weak drop-off. And what you can see, this is a histogram, what you can see is that when there is a strong drop-off in black, you have much more water that have very high iron. So in this case, the waters that are upwelled are much richer in iron when there is a strong drop-off. And in this simulation, it had a strong impact. Here is the difference of chlorophyll between weak drop-off and strong drop-off. So when you have a strong drop-off, you have a much higher chlorophyll in the coastal band due to this enrichment of iron. So the message here is that the wind structure is a very important factor in upwelling region. Okay, now I'm coming to this second example of impact of the wind. This is the impact of the seasonal variability on primary productivity. In fact, in Peru, there is a paradox. And the paradox is that there is a seasonal cycle of surface chlorophyll that is out of phase with the seasonal cycle of the wind, which is related to the upwelling strength. So this is, for instance, the seasonal cycle of the wind taken at a location from satellite data here. And you can see that the alongshore wind varies from around 3 in summer, austral summer, and reaches its maximum in austral winter around 8 and then decreases again. So there is really a maximum wind stress in winter. So there is a maximum upwelling in winter. Upwelling is really difficult to measure at the location because the vertical velocities are really weak, and there is no measurement device to measure these vertical velocities. So we use a model to study the vertical velocities. And with the model, so here we have 3 different simulations. I will not go into the details, but you have the seasonal cycle of the vertical velocity near the coast. And you can see that they are all the time positive. So there is no Dalwelling period. And the maximum is really taking place in winter. Okay, so it varies from half a meter per day up to 2 meters per day. This is average in a coastal band. So there is really a maximum of upwelling in winter. However, if you look at chlorophyll, and this is from in situ and satellite measurements, you can see that the chlorophyll is a minimum in winter. This is a paradox because what we usually think is what is usually thought for IBOS upwelling is that the more you upwell, the stronger the upwelling, the more you upwell nutrients, and the higher the productivity. So what happens in the Peruvian upwelling to explain this paradox? Well, first, there is a wind effect on the dilution of the chlorophyll. For instance, in winter, you have an increased wind, so you have an increase of the mixed layer. And also, in particular, in winter, there is less warming from the solar flux and from the heat fluxes in general. So the mixed layer tends to increase in winter, which tends to mix vertically the chlorophyll. And if you mix vertically the chlorophyll, you can decrease possibly the surface chlorophyll. So what we can do is to investigate this using a model. And so if we use a model, we can see that the model is able to represent the seasonal cycle here at the surface in red with a lower chlorophyll in winter. But then if we average, with the model, we can average the total chlorophyll content in the vertical, and we can see that this is in blue. We also have a seasonal cycle. It is less marked than the surface, but it is still true. So there is less total chlorophyll in winter. So there is a relatively small effect of dilution of the chlorophyll. So what are the other possible effects? Well, expectedly in winter, there is less light. It's not extremely strong. The variations are not extremely strong in Peru because it's very close to the equator, but there is a seasonal cycle of light. And so if you decrease the light in winter, you can imagine that you will decrease primary production because it's a function of light and also of nutrients. So what we can do also with the model is to test this hypothesis by taking no variation of light in the model. So taking constant light, like the mean constant light, we did an experiment, and what we obtain is that we still have a strong variation, seasonal variation of the surface chlorophyll when we have a constant light. And even if we look at the depth average, we also have this variation. So the seasonal variation of the chlorophyll is not explained mainly by the variation of lights. This is another thing. So seasonal cycle of insolation is not the main driver. And we can also think about temperature, because temperature also influences the growth of phytoplankton organisms. If you have a higher temperature, the phytoplankton cells can divide themselves more rapidly, and so the phytoplankton can grow more rapidly. So in winter, when you have a decreased temperature in the surface layer, the phytoplankton can decrease. But when we tested this hypothesis by taking a constant temperature, and it is not a strong driver either. So what is the main driver of chlorophyll seasonality? Well, in fact, there are two effects. As I said, the upwelling is active all year long. So you have an upwelling of nutrient-rich surface water all year long. So there is not a strong limitation of phytoplankton depth. Here in this figure, you can see that the vertical velocity, it's always positive. So we always bring subsurface nutrient to the surface. And because there is no, so first, there is no nutrient limitation of phytoplankton growth. Second, the mixed layer increases in winter, sorry. So it has a first effect on dilution, but also there is less light available for phytoplankton cells. So this is the typical limitation effect. If you increase the mixed layer, so here you have the vertical profile of light, and here you have the profile of chlorophyll. And if you increase the mixed layer, the phytoplankton will spend more time in the region where there is less light at subsurface. Okay, and so there is less light available for their growth. And so the two effects, light limitation and dilution, are the main effects that explain this paradox in Peru with this low chlorophyll concentration in winter. So to conclude, permanent upwelling, so no nutrient limitation, dilution and light limitation due to vertical mixing in winter are the main hypotheses to explain the Peruvian paradox. Okay, so maybe I will take a short break here. Agus, what do you think?
Yeah, I think this is 16:05. We take a break for we take a break for about 10 minutes.
Okay. So I will stop sharing.
Yeah, we stop for this slide. Thank you. And please, Putri, to present something, a video or something, the promotion. Halo, Putri.
Okay, before we continue to the lecture session, we will take a break about 10 minutes. We will watch a video from the Department of Marine Science and Technology. So, enjoy this video. Oke, sebelum kita melanjutkan acara hari ini, izinkan saya menyampaikan sedikit info. Saat ini Departemen Ilmu dan Teknologi Kelautan Institut Pertanian Bogor sedang membuka pendaftaran masuk jenjang studi pasca sarjana, program magister, dan doktor. Program magister dibuka untuk jalur reguler, sedangkan program doktor sendiri dibuka untuk jalur reguler dan by research. Saat ini telah dibuka tahap pertama pendaftaran sampai dengan tanggal 30 April tahun 2022. Tahap kedua pendaftaran akan dibuka pada tanggal 5 Mei sampai 16 Juli 2022. Untuk informasi selengkapnya terkait pendaftaran tersebut dapat mengunjungi admisi.ipb.ac.id atau bisa dicek langsung ke Instagram ITK sendiri, username-nya itk.ipb. Terima kasih.
Kampus terbaik, inspirasi, tebarkan harapan. Kampus terbaik, inovasi, wujudkan impian. Kampus terbaik, integritas, kuatkan tujuan. Kampus terbaik, beri terbaik untuk negeri, untuk dunia, umat manusia dan alam semesta. Mari bersama hadirkan masa depan dalam langkah dan pikiran agar selalu terdepan, berbekal ilmu dan jiwa pengabdian. Deras arus zaman takkan tertahan, majulah melangkah, oh majulah. Kampus terbaik, inspirasi, tebarkan harapan. Kampus terbaik, inovasi, wujudkan impian. Kampus terbaik, integritas, kuatkan tujuan. Kampus terbaik, beri terbaik untuk negeri, untuk dunia, umat manusia dan alam semesta. Mari bersama hadirkan masa depan dalam langkah dan pikiran agar selalu terdepan, berbekal ilmu dan jiwa pengabdian. Deras arus zaman takkan tertahan, majulah melangkah, oh majulah. Terus berpacu dalam keunggulan, lincah pembelajar untuk kehidupan. Inilah semangat baru, tekad raih kesempatan, wujudkan kampus terbaik selamanya. Mari bersama hadirkan masa depan dalam langkah dan pikiran agar selalu terdepan, berbekal ilmu dan jiwa pengabdian.
Okay, thank you very much. One video promotion and one beautiful songs created by Prof. Arif Satria, our rector. Thank you, Putri. So I think we can start again for the second session of Fangsang. And also, I'd like to remind you that if you have questions, please write down in the chat. Yeah, so we can read, or Professor Fangsang also could read the questions. Thank you very much. So again, please, Professor Fangsang.
Okay, can you hear me again?
Yes.
Yes.
I can.
Okay. Okay, so let's continue. So as I said when I was presenting the region, the Peruvian upwelling system is very connected with the equatorial region and coastal trapped waves. And so what was really interesting in recent years is that we were able to observe a coastal trapped waves using LiDAR data. So to remind you, these coastal trapped waves, they propagate all along the coast. And what we did is to place a glider here in the south of Peru here. And you can see here the red arrows are the current measured by the glider. And the glider was able to repeat a section of about 150 kilometers wide. So here is what the glider observed. So with the glider data, you have three informations. You have temperature, salinity, and also you have the integrated vertical velocity. From these three informations, you can recompute the geostrophic velocity. So this is the geostrophic alongshore velocity here, and this is the topography, and this is the time, and during the different sections. And you can see that we were able to see a poleward current. No, sorry. In blue, it is poleward. So this is in fact the Peru undercurrent. And you can see that it is getting stronger in time here. And you can see below the undercurrent, you can see this red patch here that increases also. And this is the deep undercurrent that is northward. So it was the first time that this deep undercurrent was really observed. And what we did is to take a model and try to reproduce the same kind of wave. So here we use the ROMS model. You can see that in gray, the topography is slightly different. In the model, you cannot use exactly the same topography. You have to smooth the topography. And we were able also with the same timing. So this is every 5 days. Each section is every 5 days. We were able to simulate the strengthening of the undercurrent and also the strengthening of the subsurface deep undercurrent. And this is related to a coastal wave. So now, if we look at the velocity at 700 meters, so we took a section at 700 meters of the meridional velocity. So this produces these small maps here along the Peru shore, and we look at the evolution of the 700-meter meridional velocity in time. So during about 90 days. Okay, and you can see that the velocity first is poleward in blue, and then you have at around minus 15 days, you have a strong signal in the north of Peru. Then it propagates toward the center of Peru and then to the south of Peru. So we are really in the presence of the wave that has a deep signal and that produces this deep undercurrent. So these waves, they also have an impact on the productivity because as I said, there is generally a constant upwelling of nutrients. But when a wave comes, and when a downwelling wave comes, this wave tends to deepen the nutricline. So when you have a downwelling wave, you deepen the nutricline, so you kind of compensate the upwelling. So there is less nutrient in the surface, so there is a decrease of the productivity. So you can have, in fact, when there is a downwelling wave, limitation of phytoplankton growth because of less nutrient in the surface layer. And when you have upwelling wave, because waves can have two different types, when you have an upwelling wave, you strengthen the wind-driven upwelling and you have even more nutrients, so you can sometimes stimulate the productivity. So here is the response of the effect of a downwelling wave on the system. In color, this is the current, but if you look at the black lines, here is the chlorophyll. So here, when there is a downwelling wave, you have less chlorophyll. The region with chlorophyll rich is relatively small. If you look, for instance, at this isoline, and when you have upwelling, you have a wide chlorophyll rich surface layer. Okay. You can also observe these waves looking at this kind of diagrams, which are called Hofmüller diagrams. And what you can see here is first the propagation of the signal, so the pole work operation between point A and B of sea level. So these red and blue lines, they show the propagation, southward propagation of the sea level at a velocity of 1.5 meters per second. What is interesting is that you can observe with the model the different velocity propagations of the different signals. For instance, for the thermocline, the propagation is slower at 0.6 meters per second. And if we look at chlorophyll propagation is more comparable to that of the thermocline. Okay, so now let's look at El Nino. So what happens during El Nino is that you have very, very strong downwelling Kelvin waves. So here is represented the SST anomaly during September 1997, which was during the beginning of the strongest El Nino of the century. And you can see that you can have up to 6 degrees anomaly offshore of Peru. So 6 degrees anomalies are huge. Peru is a very dry country in normal conditions. So when you have these very warm waters, you have a lot of convection in the atmosphere, and then you have a lot of rain over land, and this can produce some mudslides and a lot of problems over land. But there is also a lot of consequences over in the sea. So in the sea, as I said, when you have a Kelvin wave, downwelling Kelvin wave, you deepen the nutricline, so you reduce the primary production. And this is the anomaly of primary production measured by satellites. And you have a strong, very strong anomaly, and blue colors means negative anomaly. You also deepen the oxycline because you deepen the thermocline and the nutricline and also the oxycline, as shown by this figure of a measurement of Callao here. You also deepen the nitrocline. You can see this in this time series of the data. So the low concentration layer is much deeper here. And this has, of course, impact on the marine life. This has an impact on the anchovy. So the anchovy during El Nino events, the anchovy stock and fish catches are really reduced. what happens is not that the anchovy dies or disappears, but there is a migration towards the south. So actually, the anchovy migrates out of the Peruvian waters. And also, because there is less food for the top predators like these birds, cormorants, boobies, and pelicans, the population of pelicans decreases a lot. These birds, they don't migrate over large distance, so there is less food, and so there is a lot of starvation of the young ones, and the population decreases strongly. It can decrease over the following years of El Niño. Okay, so now let's get into more details about the mechanisms during El Niño. What is interesting is to look also at the wind anomalies during El Niño. So the gray bars in this time series show the El Niño period, and what you can see is that during El Niño there is positive anomaly. So this is quite strange because, in fact, the upwelling is stronger during El Niño. So why does it? Why is the productivity so low during El Niño? If you look, and this is really measured. If you look at observations, you can see that during El Niño 97-98, this is the anomaly of winds along the coast of Peru. You can see that there is a stronger wind of about 1.5 meters, which is relatively strong because El Niño winds around Peru are relatively weak. So what this intensification is, it's interesting. We studied also the process to explain this intensification is due to, in fact, the production of an SST gradient in the sea, in the surface layer. You have warmer water in the north than in the south of Peru during an El Niño. And so the SST gradient drives also a pressure gradient in the atmosphere and pushes the wind in the northward direction. So if you look at the alongshore wind anomalies and the SST gradient anomalies, they are very well correlated during El Niño. And this is something that we studied in detail in a recent paper with my Peruvian colleague. So if we come back to the ocean, during El Niño, we have stronger wind stress. But if you look at the vertical flux, we have negative flux anomaly. So this can strike as a contradiction. But what really happens, in fact, is that during El Niño, you have high sea level in the north, very high sea level, and a lower sea level in the south. Okay? Because why do we have this high sea level in the north? Is because the trade winds, which generally blow from east to west, they decrease. So the water, there is an advection of water, an accumulation of water toward the east side of the tropical ocean. And because you have a high sea level here and low sea level here, well, you have a geostrophic current that tends to transport waters towards the coast here. And so this is what is represented here in the model. This is the onshore current between 2 points near the coast. And you can see that it is really positive when you have an El Niño period. And you can see also that the model is able to represent this onshore current really relatively well. Here is a comparison with the Aviso, so observations of this onshore current. So what happens, in fact, during El Niño is that you have a strong wind-driven vertical flux because the wind is stronger, but in the same time, you have a strong onshore flow. And so these two effects compensate. You have a downwelling driven by the onshore flow and upwelling driven by the wind. And the result is that we have a weaker upwelling than in normal conditions. So if we have a weaker upwelling than in normal conditions, we have a weaker productivity and we have a weaker plankton. So I didn't show that. but we have also a weaker zooplankton biomass. So here the gray bars show that we can have a 30 to 40% decrease of microzooplankton and mesozooplankton. This is from model. There is not enough data to really see that correctly with observations. There is also a decrease of export, particularly of big particles during El Niño. So there is less organic matter produced near the surface. So expectedly, there is less organic matter exported at the subsurface. What is also interesting to understand why there is a migration of fish to the south is to look at particles along and the transport of particles along the coast. So here is an experiment done by using the ROMS model, where particles are released in this black box near the coast, and they are transported during 1 month. So they were released here at the beginning of this in November, and we look at the particle in December. First, if you look on the left side, this is December 95, sorry. So this was a normal year, not El Niño year. And you can see that the particles were expectedly, because of upwelling and Ekman transport, they are mainly transported offshore, okay? Then, if you look at an El Niño year, like December 97, because you have a strong along-shore current during El Niño, these particles are transported all along the coast here to the south. So if you have fish larvae in this region, which is very rich with fish, this larva will tend to be transported toward the south, and so will either die or also, if they manage to survive here, they will be further south, and this also explains partly of the migration. Okay, so now let's go back to another impact of El Niño, which is very important, is the impact on oxygen. So as I said, when there is an El Niño, there is warm water coming towards the coast and a deepening of the nutricline, and there is also a deepening of the oxycline. So here is, we studied this using a model. So here is pictures showing that the model is relatively behaving well. This is the OMZ upper limit. It is around, it's 22 micromole, the depth of this surface. So you can see that the model is representing it well. And if we take a section, a mean section over the system, you can see that the model is representing the oxygen minimum zone relatively correctly with slightly lower oxygen values in the model. And then during El Niño, and this is the anomaly of the concentration, during El Niño, you have more oxygenated water in the surface here with positive anomalies of around 10 to 20 micromoles. And the model is able to represent this also really correctly. If you look at the time series of oxygen, so it's an opportunity to look at the data from IMARPE. You can see that we have a long time series in blue. And we can see with the gray bars that the model is also representing the deepening of the upper limit of the oxygen minimum zone. So the oxygen minimum zone sort of migrates vertically during El Niño. If we look at the position of the oxycline, well, the position of the oxycline is really correlated with the thermocline, and we can see that this correlation is really related to the pathway of coastal waves. It's correlated in the south over the Peru region and Chile region, but also in the north over the coast of South America, because you have waves going towards the north and towards the south. And so there is during El Niño, there is a deepening of the oxygen layer of the oxycline and of the thermocline in the south and in the north. Another effect that has been investigated more recently is the effect of the eddies. So here I show you a time series of the eddy kinetic energy offshore of the Peru coast. And you can see here that there is a peak during El Nino. What does it mean? It means that during El Nino, in fact, you have stronger eddies in this region. What these stronger eddies do is tend to mix the surface and subsurface water. And what they tend to do at subsurface is they tend to bring oxygen from around the oxygen minimum zone into the oxygen minimum zone. So here is the arrows, they show the flux of oxygen due to the eddies. And you have a strong flux on the southern flank of the UMZ. And during El Nino, here you have a stronger flux. And also at depth, you tend to have the stronger flux during El Nino. So what it means is that during El Nino, because the eddy activity is stronger, these eddies, they tend to mix oxygenated water into the OMZ. Okay, so now I'm going to go to larger, longer time scales, decadal and climate change. And I will explain the impact on coastal winds, but also, and I will skip some slides. I will explain the impact on the OMZ, and then on the planktonic biomass and small pelagic larvae. So I worked a lot on this subject in three projects, two French projects with collaboration with Peru, and one project that was mainly managed led by IMARPE. Okay, so I will skip this part, sorry, and come directly to the impact on the oxygen. So what drives the oxygen variations, the long-term variations in the Peru upwelling systems? We studied this with my colleague, with a Peruvian colleague, and I will present some results about the long-term trends. The long-term trends in the past, so decadal trends. What we did is to study this with observations, but with a model, with a long simulation over the period 1958-2008. So what is the context? In fact, if you look at the recent surface temperature data from satellite, for instance, between the 80s and 2014, what we can see, if we look at the trends, what you can see is that there is a surface cooling over the most part of Peru, and it is slightly stronger in the south of Peru, and also in the north of Chile, as represented here. If we look at the chlorophyll over a long time series here, for instance, in this region, we have a positive chlorophyll trend. And then if we look at the oxycline trend, we have also, in the recent period, we have a shoaling of the oxycline, which means that the very oxygen poor waters tend to get closer to the surface. So we have consistent trends in surface temperature, oxycline, and chlorophyll. And they tend to tell us the story that there is maybe more upwelling. So there is colder water, more cold water that is upwelled, so the SST tends to decrease. There is more upwelling, so more nutrients and an increase of chlorophyll. So, and the last part is that more upwelling means closer oxycline to the surface. So this kind of tells us that this is the story. But we try to look at the forcing of these trends in more detail. So if we look in details at the data and at the model, at the trends, so here we have the oxygen trends computed over this period of almost 30 years. what we can see is that the trend is stronger around 50, 70 meters. The red bars correspond to the observations, and the black bar corresponds to the model. So first, we can see that this trend is stronger around here, around this depth. But also, what you can see is that the model is relatively good to represent this trend. So we can use it as a tool to investigate the mechanism. And if we look at the trend average over this coastal box here, and we look at the time series, we have here in red the observations, and here in black the model, and we can see that the trend is relatively well represented with around a trend of around 9 meters per decade in the oxycline and 8 meters per decade in the observation. What is also interesting is that, okay, with the model, we have all the data that we want. But if we take in the model only the profiles that were actually made in the ocean during the cruises, we tend to have a stronger trend. It means that the model is probably overestimating the trend a little. Okay, so what we did is to test two possible drivers of the oxygen trend. One possible driver is the local wind. So the local wind stress, local wind reinforcing here. And the other possible drivers are the currents, the offshore currents, the equatorial undercurrent, and the two counter currents that tend to bring oxygen-rich waters towards the OMZ. And what you can do is kind of switch on or switch off the variability of these two forcings. So in the first experiment, what we switched off is the trend of the wind forcing. So the wind forcing is climatological and regular, and there is no trend in the wind forcing. And we kept the variability, the internal variability in the boundary conditions. So the equatorial undercurrents, they have this trend. And what you can see is that we obtain a relatively strong oxycline shoaling. And if we turn off the internal variability of the boundary conditions of the jets here and keep only the internal variability of the wind, we obtain a very weak shoaling of the oxycline. So this means that the main drivers of the oxycline variations are not the local winds, as we may have expected, but they are the variability in the equatorial Pacific of these equatorial currents. And this is quite important because this variability is not well known. There are few measurements in these regions, and also the models tend to disagree on the trends of these equatorial currents. So in conclusion, the reduction of oxygen flux by the equatorial currents is the process that induces deoxygenation in the Peru Ubus. Okay, let's get now to climate change. So to study climate change, what we usually do is to use different scenarios, climate change scenarios. So I think most of you have heard of these climate change scenarios. For instance, there was this CEMIP-5 exercise a few years ago that did a lot of scenarios with different emissions. So there are like optimistic scenarios where there is a reduction of the radiative forcing related to CO2. And there are also like pessimistic or worst case scenarios like the RCP 8.5 scenario, where there is an ongoing increase of CO2 and an ongoing increase of the radiative forcing. So the question was, what happens in the Peruvian IBUS? Well, first, if we look at these climate models that are used in the CEMIP exercises, they generally have a very low resolution, and they do not represent correctly the processes in the upwelling systems. So for instance, if we look here at the surface temperature in one of these models, the IPSL CM5 model, which is a French model, what you can see is that there is no cold water along the Peru shore, which means that the upwelling almost does not exist in this model. If we look at the temperature in observations, we have this very, very cold water. So this is not represented in the model. And so there is a necessity to use regional model to downscale these climate signals. So what we did in this project is to downscale 3 CMIP5 models. We selected 3 of them: the CNRM model, the GFDL model, and the IPSL model. And we used a Ramsey-Pisces model configuration at 10 kilometers in the Peru region. And we downscaled only the worst case scenario. So it may seem like we didn't do a lot of work, but in fact, it's really a lot of work to do long-term simulations, and we run the model for hundreds of years. Okay, so let's look at these 3 models. If we look at the wind stress in this box here, what we can see is that 2 of the models indicate a decrease of the wind stress intensity, meaning that there will be a less upwelling in the future, wind-driven upwelling in the future. Okay, and one of them shows no amplification. So this is an important result, because in the past, like in the 90s, papers by Bakun said that upwelling would increase in most EBOS. And this hypothesis has been criticized a lot more recently. If we look at the upwelling, so the vertical flux of water in a coastal box, we can see that it responds correctly to its expected response due to the wind stress evolution. So we have a weak evolution for the blue curve, which is the GFDL model, and we have a strong decrease of the upwelling in these 2 models. What is really important now is to look at the temperature, and we can see that we have an increase of temperature in all the models. So this is important, because even in the case where there is no decrease of upwelling, which is the blue curve, we have an increase of temperature. And in fact, how can we explain that? It is because the water that is upwelled in the box here, so the subsurface water, tends to warm in all the scenarios. Okay, so it's warmer, the increase is stronger for the IPSL model, up to 4 degrees, which is really huge. It's an important, probably a very important impact on the ecosystem. And the lesser increase is about 2 degrees. Let's now look at the response of the biogeochemistry. If we look at the nitrocline depths in global models, CMIP5 models, here in green, I have put the nitrocline depths from IMARPE data, from observations, okay? It's around 20-meter depth. Then if you look at the models, like the global models, which have biogeochemistry in them, the nitrocline depth is around 60 to 100 meters. So you can see that there is a very strong bias in these models. So it's kind of difficult to trust them. So if we use this Ramsey-Pisces model to downscale these large-scale models, we are able to correct a great deal the bias of the nitrocline. So in the years, recent years here, 2010, 2020, we have a nitrocline in this Röhmspies simulation, which is around 20 to 40 meter depth, which is relatively correct. And then the evolution of the network line depth is very different in the different models. You can see a very strong deepening in the CNRM model, and a moderate deepening in the IPSL model, and a slight shoaling of the network line in the GFDL simulation. If we look now at the surface chlorophyll in the global models, here on the left side, you can see that the trends are all decreasing trends, surface chlorophyll. And also you can see that they are very different levels. You have mean chlorophyll levels around 0.1, 0.3, and 0.7. But in fact, in the real world, satellites tell us that the surface concentration is around 3 to 4 milligrams of chlorophyll. So there is almost an order of magnitude of error in the global models. Whereas if we use the Röhmspies model, we are able to represent relatively correct levels of chlorophyll, between 4 and 6 milligrams of chlorophyll per cubic meters. Okay. Now, what is also very interesting is to see that the trends are very different. Whereas all the models show decreasing trends, now we have almost no trend for 2 models, and we even have a small increase for 2 other models. So this is kind of puzzling because, for instance, if you look at the red curve here, there is an increase of surface chlorophyll, whereas there is a decrease of the nutrients. Okay, so here we begin to see that there are complex processes that may compensate each other. So if we look now at the vertical structure of chlorophyll, we also learn interesting things. What we can see is that the trend for the surface chlorophyll can be positive, but in fact, in the subsurface, it is negative. Okay, and this is kind of a robust result in the 3 models, even in the GFD model. So this is an important matter because it tells us that if we observe the evolution of surface chlorophyll from space, for instance, over long time scales, maybe we don't know the entire story because subsurface chlorophyll can decrease and it will not be observed by satellites. Okay, so to summarize the results, we have less upwelling in in 2 of the models. So there is less upwelling, less nutrients in the euphotic layer, but there is also less offshore transport because the Ekman transport is reduced. So maybe there is less phytoplankton that is produced in total, but this phytoplankton can stay more near the coast. There is more retention near the coast. So because also there is more stratification and the shallower mixed layer, there is kind of a stable phytoplankton concentration at surface, which explain these trends, which are weakly positive. And but there is a reduction below the surface layer. Okay, so I think I will skip this part because I don't have enough time. And I will tell you a few words about the fisheries. So the timescales of the variations of fish are very strong, are very important. You have seasonal and internal timescales with El Niño, but also decadal timescales, which are shown here by the anchovy with the black squares and the sardines with the small squares. There is also a measured variability of zooplankton, for instance, here with euphausiids and small zooplankton that has been measured by IMARPE colleagues. What is also interesting is that you can measure variability in the upwelling system using sediment cores. And you can access two timescales that are much longer, like millennium timescales. And here I'm showing an example of the centennial timescales, where here you have a proxy of diatoms here, and this is the time. So we have the evolution between 1300 and 2000. And you can see a very important shift in around 1830. And this shift has been related to a northward shift of the ITCZ, so a climate shift in the Pacific, and also a northward shift of the Pacific subtropical high, which induced a stronger coastal upwelling, and so a richer upwelling, more diatoms, more big phytoplankton. This has also an impact on the fish productivity. And here what has been counted in these sediments is the fish scales. And if you count the fish scales, you can have a lot of information. And you can see that there is an increase of anchovy after the climate shift. And there was also an increase of sardine in this period and of some offshore species, warm water species. Okay, so now let me get back for a few minutes on the Peru paradox of productivity. So Peru produces more fish per unit area than any region in the world, but it represents less than 0.1% of the ocean surface, but produces almost 10% of the world fish catch. So how can this be explained? Well, the first explanation is about the wind intensity. In fact, there is an optimal environmental window for recruitment success in a upwelling area. Recruitment means the success of survival of the larva. Recruitment is what is called the amount of larvae that can grow as adults. So in this schematic, what you can see is that there is an optimal window due to the wind intensity. In fact, if there is not enough wind, low wind, there is not a lot of upwelling, so there is not enough nutrient to sustain a high productivity. On the other hand, if you have very strong wind, you have a lot of turbulence. So the larvae can be mixed vertically very strongly, and they have difficulty to eat, to forage on their prey when they are old enough to eat. And also because there is a lot of turbulence, there is a lot of export of larvae offshore, and there is a lot of loss of eggs and larvae when they are exported offshore. They are not in the region where there is enough food to survive, and there are also there is also a lot of predators. So this optimal window of 5 to 6 meters per second wind is what is favorable for Peru. Related to this is the upwelling strength. So the upwelling strength is related to the Ekman transport, and here is the formula of the Ekman transport. It is proportional to the alongshore wind stress, and it is also inversely proportional to the Coriolis parameter. What happens is that also that Peru is close to the equator, so F, the Coriolis parameter, is relatively small. So if you have a relatively weak alongshore stress, because F is small, you can have a large Ekman transport. So a large Ekman transport can be obtained with a relatively weak wind. So this is favorable for the optimal window, and also it produces a large Ekman transport, so there is a strong enrichment and relatively low turbulence. So this is favorable to the larva. One historical hypothesis has been proposed by Rather in 69 is that the anchovy would belong to a short food chain, since it forages directly on primary producers. So for a long time, it was thought that because anchovy eats mainly phytoplankton, it can grow very fast and thrive in this upwelling system. But in fact, this hypothesis has been challenged recently by Espinosa and Bertrand. What Espinosa and Bertrand did is to analyze the stomach content of fish, of anchovies, of 20,000 anchovies. And what they found is that the majority of the food that is found in these stomachs is not phytoplankton, but it's more zooplankton, copepods, and euphausids, which are a very rich kind of food. So in fact, anchovy forages mainly on zooplankton, so the short food change is not the explanation. What are the other hypotheses? Well, as I said, there is all year upwelling, so there is food all the time for the larva. There is anchovy spawning during the high upwelling season, so it is favorable to the larva. The food that is consumed by anchovy is euphausids, and they are highly energetic, so it is favorable for their growth. And also, there is also a hypothesis about the habitat of anchovy. As I explained, there is a very intense and shallow oxygen minimum zone, and life concentrates in this thin and shallow layer at night. So for instance, here you have an acoustic image showing that you have zooplankton here in blue and anchovy here in red. And so because all this life is constrained in the very shallow layer in the Peru region, it is favorable for predation. And so anchovy has a lot of food and can grow efficiently. Okay, so I'm getting to the conclusions. I couldn't show everything, but I will talk about some open questions and perspectives on the upwelling system. So about the impact of climate change, as you saw, we only downscaled 3 semi-5 models. So 3 models is not enough, and we need to probably downscale more models to reduce error bars related to climate change. Also, there are new scenarios in CEMIP6, for instance, the recent climate simulations. And also there is a problem that I didn't mention about wind downscaling. Wind downscaling is important. It is not always done, and we have to improve the methods to do that, as the winds are a very important forcing for the Peru upwelling. I didn't mention that also, but there are very small scales in the ocean. Here is an example of a picture of the very small scales around eddies. And you can see that if you use a model which has a 4-kilometer resolution, you completely miss the very small eddies and filaments that can exist in the simulation. And these eddies and filaments, they play an important role in the productivity, but also in the oxygen minimum zone ventilation. They can transfer surface oxygenated waters into the subsurface layers. As I mentioned, there is a need for wind measurements near the coast to reduce errors. For instance, here I show you an example. If you take one grid point of satellite data offshore, you have a seasonal cycle that is well known of Peru. But here, very near the coast and near this bay here, the seasonal cycle of the wind is very different due to the land-sea thermal contrast. And so we really need to have observations and high-resolution models to simulate, represent the wind in this band, which is very important for upwelling. Then again, we need to use regional models and high-resolution models to study the processes from plankton to fish. They are called end-to-end models. Just to give you an example of the recent papers that have been published to study the impact of climate change on the total consumer biomass. So it's all the fish in the ocean. So here it's scenarios without fishing activities. And you can see the difference between the year 2050 to 1990s. And all the red is the negative effect. So telling you that there will be less fish available in the ocean because of climate change. But what you have to keep in mind is that, for instance, for Peru, what is used is these large-scale climate models that do not well represent the upwelling processes. So we need to have end-to-end models with high resolution. And this job is really to be done in the future. Then I didn't mention the small scales, but a lot of human activity concentrates very near the coast in upwelling systems. For instance, in coastal bays of Peru, you have a lot of fisheries and agriculture activities like Peruvian scallop farming, and it's an important resource for economy, for the Peruvian economy. And then in these small bays, you can have new and complex biogeochemical processes. For instance, when there is very low oxygen, you can have production of H2S from the anoxic sediment here, and you have measurements of H2S in the water column. And this H2S, when it propagates to the surface, it can coagulate and it can be observable from space, what is called aguas blancas, and in Spanish, white waters. And these processes, these complex processes, are not fully understood, and they need to be studied, and also in the context of climate change. So with this, I'm finished my talk. Thank you very much for listening, and I'm listening to your questions.
Thank you very much, Professor Wang Sang. This is a wonderful and very impressive lecture this afternoon. I think maybe this is actually for 4 or 5 lectures, but you gave about 90 minutes. Yeah, and this, you already explained very comprehensive lectures on IBUS Peruvian upwelling system. And I searched here around 100 participants already stay, but just left about 10 participants in the last minutes. Okay, please, a question to Professor Wang Sang. I think from chat, Dr. Adi Purwandana asked you a question. Professor Wang Sang, can you read the chat?
Yes, I will try to read it.
Yeah, please.
You want me to read the question? So the question is there a connectivity study discussing the connectivity between upwelling events and turbulent vertical mixing processes? How do they interact with each other? Is the vertical mixing driven by shear vertical variability of the eastern boundary current? Okay, so to my knowledge, there hasn't been a lot of studies on this matter. I think it is particularly because there has not been a lot of measurements of turbulent mixing in this region. In fact, my Peruvian colleagues, to my knowledge, they do not have the devices to measure vertical mixing, even though it's quite important. It has only been measured by German colleagues, and there are very few papers about that. I think there are a few papers. There is one paper that relates the vertical mixing near the coast, not to the variability of the eastern boundary currents, but more to the internal wave activity, which is quite important on the Peruvian shelf. So I hope this answers your question. Okay, and the second question is, as we all know that 2020 to the end of 21-22 is extreme La Nina years. What is the current condition of upwelling on the west coast of Peruvian water? How does the upwelling type mechanism occur? How about monsoon systems contribution? Is there a significant difference from the upwelling process in general in a Peruvian water? Okay, so first about La Nina. Yes, so there is a La Nina year recently. I didn't mention La Nina because, in fact, La Nina has less been studied in Peru because its consequences, its impacts on the Peruvian upwelling system, fisheries particularly, are not strong. In fact, La Nina is more like an intensification of a normal year with more upwelling. And as I said, the Peruvian upwelling is very, very productive in terms of nutrients. There is a lot of nutrients. So during La Nina year, there is even more nutrients, and the productivity has a limit. It cannot increase much stronger. What happens is that it can be slightly decreased in winter when you have stronger winds because of this process, vertical mixing process that I mentioned. If the winds are stronger during La Nina year, you can have a deeper mixed layer and a more important light limitation during La Nina. So then, the question refers to a comparison with monsoon systems. Well, the monsoon systems are really different because they have two phases with an upwelling phase and sometimes a downwelling phase. Well, in Peru, what is particular is that it's upwelling all the year. And there is a seasonality, of course, with stronger winds in austral winter. But even in summer, there is always upwelling. And actually, summer is the most favorable region for production because you have sufficient nutrient and you have a lot of light, you have warm waters, and you have relatively shallow mixed layers. So you don't have this limitation by mixing. Okay, so there is another comment. So the Peruvian upwelling system has been studied for a long time, since the 50s. Is there any change of the characteristic of the Peruvian upwelling system based on data collected not from the model? If this is the case, what factors affect this change? What is the impact of this change for current Peruvian fishing activities? Okay, so yes, it's true that it has been studied for a long time. In the study of the impact of recent change on based on data, what is known is the impact on oxygen. So there is really a deoxygenation over the last period in the Peru region. over the last 20 to 30 years, there was less oxygen near the surface. But in the recent decade, it seems that there has been a small increase of oxygen again in the surface water. So there is a decadal change. As I have showed, there is a lot of data on the fisheries, on the top higher levels of the food change, and there has been decadal variability of sardine and anchovy in the last 50 years. This decadal variability is partly explained by the long-term climate variability that I didn't talk about, which is the Pacific decadal variability. I'm not an expert in that. I think it's a complex problem, and it's also related to large-scale variability because you have similar decadal variability of sardine and anchovy on the other side of the Pacific. And so the processes are not particularly related to what happens in Peru. The last question, it was the impact of this change on Peruvian fishing activities. Well, these changes are monitored with a lot of scrutiny by the Peruvian fishing activities. This is why IMARPE has been created so long ago, is that what they are trying to avoid is, for instance, overfishing during El Niño years. So as I showed, during El Niño years, there is less fish. And there is, if you overfish during these periods, it can really make the stock to collapse. So there has been ongoing collaboration from Peru with other institutes, and particularly with IRD fisheries specialists or scientists, to try to monitor these fish populations. So I hope this answers your question. So there is a comment by another person. I'm interested in one of your slides where you show changes in the chlorophene concentration around Peruvian Uibos, and there is a shift in phytoplankton abundance. Okay. Have you or others observed whether there are higher frequency in algal blooms, coastal and oasic blooms, in relation to climate change or changes in the characters of nutrient upwelling, like changes in oxycline, nutricline, and thermocline? Okay, so we have not. What I can tell you is that we didn't really look at the frequency of algal blooms in these simulations with climate change. We really looked at maybe longer time scales, seasonal time scales, or decadal time scales. So I don't think, to my knowledge, that this has been studied in the Peru upwelling system. Okay, so I hope I've answered your questions. There is another question about the OMZ ventilation. How does small-scale eddies and filaments contribution to the OMZ ventilation compared to from major current? Okay, so this is something that I did not describe. So in the oxygen minimum zone, you have ventilation, as I said, from the offshore currents, the near equatorial zonal jets that are large-scale currents, that transport relatively oxygen rich to the OMZ region. And what happens is that you have also within the OMZ, you can have a lot of eddies and filaments. What these eddies do is that they tend to stir water, and the eddies that are at the sides near the boundaries of the OMZ, they tend to exchange oxygen-rich water from outside into the oxygen-poor water inside the OMZ. So this is the horizontal process. Then if you look at filaments, so upwelling systems are one of their characteristics is that they have a lot of cold filaments near the coast. And these filaments, now that have been observed from space for a long time, now we know their dynamics a little bit better. And in fact, we know that they they tend to have a subsurface component, and they tend to downwell surface water to the subsurface. So what happens is that because of these filaments, they can transport oxygen-rich waters towards the core of the subsurface layers of the OMZ, and they tend to ventilate it in this way. And this is an important contribution. In fact, they tend to have a more important contribution than the mesoscale eddies, for instance. This is, I didn't mention that, but this is a study that we are doing. So this kind of studies can be sometimes observed. This kind of process can be observed sometimes with observations, but you have to be lucky because you have to have, for instance, a glider intersecting a filament, which is not always easy. But what is mostly done is that we use high-resolution models to study this kind of process. And what is it? If I want to go on this point, is that it's interesting also because these filaments, they tend to downwell surface water into the subsurface waters. So they also transport the nutrient-rich waters at subsurface. So they tend to decrease, in fact, the production, because they tend to take nutrients from the nearshore waters and put them at depth offshore. This has been shown with observations, and this has been shown also with a lot of model studies.
Okay, thank you very much, Prof. Bangsang. So all the questions, Dr. Adi Purwandana, maybe I think you know is the Professor Pascal students, former Professor Pascal student, also Dr. Andri from BRIN, Dr. Adi from BRIN, Professor Bangsang, but here Bangsang Siregar, Professor Bangsang from Bogor University, Dr. Arif from BRIN, and the last question from Dr. Faisal from BRIN. So BRIN is like the new institution for the research scientists in Jakarta. So it's very excellent research center. I think hopefully we can conduct the next collaboration. My question maybe, you have you mentioned that different seasonal variation of the magnitude of the winds. During winter is much stronger, during the winter much stronger than summer. But this is no change in direction of the winds. The wind is still flow from south, the southward. That's it. The second question is you saw the hypoxia layer. This is just below subsurface. So I guess that the anchovy fish stay in the upper layer, just just near the surface. That's right.
Yes. Yes, the anchovy is mainly in the upper layer, but sometimes it can be in the it can spend some time in the anoxic layers, a limited period. I'm not an expert on this, so I won't go into the details, but there has been evidence of that.
Okay, thank you. And the wind direction, not reverse.
Yes, you're right. So the wind direction is mainly parallel to the coast, along all the coasts, which makes it like it creates a permanent upwelling during all the year.
Okay. So I mentioned before that that is very different with our upwelling here because monsoon winds reverse twice a year. Yeah, sometimes so one season upwelling, one season downwelling. Thank you very much again, Professor Fang Sang. I think time is very limited, so I give to Putri. Maybe yeah, please, Putri. Mute, still mute.
Iya, Bapak. Okay, at the end of the discussion, we will give a certificate to our moderator and keynote speaker. The first one, we will give to our moderator, Dr. Agus Saleh Atmadipura.
Thank you.
Okay, this is the certificate to our moderator, Bapak Dr. Agus Saleh Atmadipura. Terima kasih banyak Bapak atas kesediaannya sebagai moderator dalam webinar hari ini. And the second one, we will give a certificate to our keynote speaker, Professor Pin Hyong Shovin. Thank you for your time and your delightful lecture. Okay, ladies and gentlemen, we will finally come to an end. Those are the agendas we have presented to you this afternoon as we have finished our today's webinar. We hope you to learn something from this webinar. Thank you so much for your attention. See you on the next occasion. Have a good day. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Thank you very much for all participants. If you need the material presentation or also recorded video streaming on YouTube, you can access directly. Maybe the local committee will inform you later. Yeah, and also for the material presentation. Thank you very much for all participants and also Professor Fang Sang. Special thank you very much. This is the first time. Hopefully you come to Jakarta. I already contacted the Jakarta. This is new representative, but he is not yet come to Jakarta. Thank you very much for all participants. Have a good day, good afternoon, and bye.
Thank you, Monsieur Song.
Professor Fang Sang, itu double Fang Sang ya.
Moi aussi Fang Song. Je m'appelle Fang Song, but
I'm not really a professor, by the way, but it's okay.
Yeah, in the next future time, man. In the next time, you will be a professor.
Now he is the research professor, Professor Research, because from IRD. Yeah, I think same here also.
But
he's already SDR in 2013. Yeah, it's a long time ago.
But in
Okay, thank
France,
you very much.
we call it also Monsieur le Professeur already.
In fact, professor is
Direct.
really the people who teach at university in France, and I don't teach at university.
I see.
But it's okay. You can call me a professor if you want.
Very, very humble person.
Okay.
Thank you. Professor Bangsang Siregar also, he was graduated from Brest, yeah, Brest University, UFO.
Yeah.
Okay, thank you very
Okay.
much.
See you, Monsieur Shafan. Merci, Pak Agus.
Thank you, Pak Vincent. See you, bye.
Mahasiswa, masa yang indah, berjuta kenangan dan impian dan harapan. Masa ini menempa diri, raihlah ilmu dan jiwa pengabdi. Siapa dirimu, bangun negeri, kemas masa ini, lewati bersama karya gemilang, kaya prestasi. Tuhan tunjukkan padaku langkah untuk maju, untuk mengukir sejarah baru.
Oh gitu, oh iya. Biasanya kan aku pakai internet aja. Nah,
Masa yang indah, berjuta kenangan dan cerita, bertabur impian dan harapan. Masa ini menempa diri, raihlah ilmu dan jiwa pengabdi. Siapkan dirimu membangun negeri.
Bagi gue pinter itu nggak cuma soal IPK, tapi juga soal sosialisasi. IPK 4 tuh gak harus ambis banget cuy, gak harus dipikirin banget. Santai aja, nongkrong aja, yang penting lu rajin dan percaya diri.
Halo teman-teman, kalian tahu nggak sih dari total penduduk Indonesia hanya 0,2% saja yang berinvestasi, sedangkan negara Singapura hampir 30% rakyatnya berinvestasi. Belum lagi mahasiswa saat ini akan diwariskan oleh middle income trap, di mana pendapatan akan stuck di level menengah. Sudah saatnya mahasiswa untuk fasih manajemen keuangan.
Selama 20 tahun hidup, gue tuh paling ngerasa gue banyak belajar ketika masa menjadi mahasiswa, yaitu masa-masa saat ini. Kenapa? Karena ketika saat ini gue banyak banget nge-challenge diri gue, dan juga gue banyak banget ngikutin dan ngambil kesempatan-kesempatan yang gak pernah gue berani ambil sebelumnya. Jadi gak usah takut ketika lo jadi mahasiswa untuk ngambil kesempatan ataupun men-challenge diri lo, karena itu adalah bagian dari lo belajar.
Sebagai mahasiswa, tanpa sadar pendapat kita pasti bisa merubah sekitar. Jadi, siapapun kamu, jangan pernah merasa pendapatmu sepele atau tidak berarti. Your opinion does matters. Tapi jangan lupa juga untuk selalu bertanggung jawab atas pendapat yang telah kita utarakan. So, voice your opinion responsibly and see your surroundings change.
Kemasan masa ini, lewati bersama karya gemilang, kaya prestasi. Tuhan tunjukkan padaku langkah untuk maju, untuk mengukir sejarah baru. Karya gemilang, kaya prestasi, kaya prestasi. Pada aku, langkah untuk maju, untuk mengukir sejarah.